So this video is going to summarize questions 9 to 16 and clarify some things for you. So the properties of a longitudinal wave can affect the sounds that we hear. And so in the how high, how loud simulation, let me go ahead and click that here. And you can actually click this link yourself or copy it, if you will. I'll put it in the Google slide for you in the section header. And if you scroll down, you can just click on the interactive and you can record yourself saying you at different volumes and different pitches. Okay. But what you're going to find out. Okay. So if you go back and watch that video for questions, I think 9 to 11. Okay. You see that in that video, when I did say the word you, I was able to change my volume. And so I can do that real quick. So you. Okay, so you can see here that I tried to keep my frequency about the same. It did get a little bit higher, but you can see where my volume changed because the amplitude got higher. And so what pattern do you observe in the oscilloscope? Well, you should see that in that graph that the amplitude changed because my volume changed. And so this tells us something about the relationship between amplitude and volume. There's a direct relationship. The higher the amplitude, okay, means it's transporting a higher amount of energy. And since they're transporting higher amounts of energy, the particles of the medium, they're able to vibrate harder and do more work, which translates to a more intense sound that we recognize as a louder volume. Now, loudness or volume is measured in decibels or dB, and amplitude is equal to volume. So, what property determines the volume in a sound wave? It's going to be amplitude. And so what you're going to see here is just some noise level comparisons. So breathing has a sound level of about 10 decibels. A quiet office, maybe a classroom of maybe 50 decibels. A noisy restaurant or street traffic would be about 70. Your alarm clock would be 75 decibels. And you can see as the amplitude increases, okay, the energy level is increasing. So at 90 decibels, notice that this can cause hearing loss. Sustained exposure to 90 decibels can damage your eardrums. 120 decibels. So that's a lot of energy. That's where pain is going to begin in your ears. Sandblasting or a rock concert is 115. If you've ever been to a concert and you walk out and your ears kind of feel fuzzy, this is why. Because all that energy was pounding those eardrums and it's disrupting those particles. And that's why you feel funny when you come out of a concert, okay? At 150 decibels, your chest wall is going to begin to vibrate. At 160, your eardrum is going to break instantly. And I'll talk about here in a minute how you hear. Death of your hearing tissue is 180, and then the loudest possible sound without distortion is 194. So what this tells us, guys, be careful really when you're listening to your headphones on a high volume, or you're in the car with your parent and you're jamming out and you got that volume high. That's okay sometimes, but if you consistently do that over time, you can ultimately damage the hearing tissue in your ears, and you could have hearing loss before you're 50, before you're 40, before you're 30. Okay. So not only does this tell us, the more energy, the more amplitude, but it kind of, applies to real life situations as well. So that's something to think about. Okay. Sound properties can also be determined by frequency. And so I did another video for you to help you answer questions, I think 13, 14, 15, maybe. I'm kind of losing track, but I'll play another video for you. So the pitch of a sound is a description of how high or how low the sound seems to a person. So you might describe somebody as really pitchy because they're like their voice is so squeaky and high, or maybe they've got a low pitch because they're uh got this deep voice. Okay, so there's the difference between pitch. Pitch depends on the frequency of the sound wave. Now, the higher the frequency, the higher the pitch. And the lower the frequency, the lower the pitch. And I can show you this in the simulation real quick as well. So I'm going to record a hi. I'm actually going to do you. Okay. And you can see that I got 3 waves for 5 meters per second. And then I'm going to do a low pitch down here. You, you. I really need Mr. Holtgrew or Mr. O'Donnell to do this. You. Okay, so you can see that my waves per second significantly decreased when I change my pitch there. So let's go back to this. Now, most people will hear frequencies between 20 hertz and 20,000 hertz. We can't hear anything below 20 or above 20,000. But some animals can hear, and we'll see a graph an illustration in just a second. Sound waves with frequencies above the normal human range of hearing are called ultrasounds. You've probably heard of ultrasound in hospitals. So mothers who are pregnant can go in and get an ultrasound of their baby. And what that ultrasound is actually a picture using sound waves. And we can't hear those. Sound waves with frequencies below the normal human range of hearing are called infrasound. Some examples of infrasound would be elephants stomping. So when an elephant stomps, it can send a sound wave through the ground. We can't hear them, okay? But elephants can feel those vibrations from miles away. And we call those sounds that we can't hear below 20 hertz infrasound. Okay. All right. I am not going to I'm not going to do this with you. This is something you can do. This test is really fun. I suggest you do it with your family, like just sit around the computer. And what you're going to do, if it'll load, you'll play the frequency test. When you start to hear the frequency, okay? When you start to hear it, if my computer is going crazy, you and your family members can raise your hand, okay? And then when you can't hear the frequency anymore, you put your hand down. Now, according to this, we're past 20 hertz and we should hear this, but I hear nothing. And I think that's because you need headphones in to hear that low frequency. If I be quiet, maybe we can start hearing it together. This goes on for 6 minutes, and I'm not going to do this for 6 minutes. I think around 125 is where we can hear it without using headphones. This is my favorite thing to do in class with you guys. So you can see the frequency is low because that wavelength is really short. And as the frequency starts to increase, that wavelength is getting shorter. Let's see if I have my volume up, so maybe you can hear it. I wish my internet would stop lagging. So in the classroom, we would start hearing this over my loudspeakers, but I'm on my computer, so I can feel the vibrations in the computer, but I still can't hear it yet. Oh, there it goes. So I can hear it. Can you hear it? And so this is going to go on for a while, and you can see that wavelength is getting shorter and shorter as that hertz, the frequency is going up. And you can hear how the sound is changing because it's getting faster and faster. And so I'm going to kind of skip. I don't want to skip. I love this. It's so fun. So I'm going to go ahead and pause this because I don't want to give anything else away. But just sit around the table with your family and you guys kind of do this together. This is going to go on, like I said, for 6 minutes. Well, right now mine's going to just stop for me, but sit around the computer and you guys as a family take that test and see who has hearing damage and see who can hear the sound the longest. But remember, around 20,000 hertz is when you're going to stop hearing it. Nobody can hear over 20,000 hertz. Okay. I'm going to talk to you just for a second about resonance. This is just something a little extra. What resonance is, it occurs when the frequency of a sound wave and the natural frequency of an object are the same. So suppose an opera singer sings a note that has the same frequency as the natural vibration of a crystal glass. If the note is played steadily, so if that opera singer can carry that out for a long period of time, the sound waves from her voice can add to the amplitude of the vibration of the glass so much that the glass shatters. And I have a video for that too. So I don't think that's going to let me click on it. So let me get out of that. Okay. And I'll share the link to the PowerPoint so that you can click these videos and use them. But they're going to play a note, and no, it's not an opera singer. And this note gets played steadily. Ooh, that's loud. And it's vibrating the glass, and the note, the amplitudes are going to match. And when that happens, if you increase the amplitude, then you're increasing energy, causing that glass to eventually break. There it goes. So that's what resonance is. So that was just a little extra, something fun to learn. What we're looking at here is the hearing ranges of various species. And I love this. And there's many charts out there. You can go Google frequency ranges of animals or something like that, and it'll give you different things. So if you look down here at the bottom of the graph, you'll see a 0 frequency to 100,000. Remember, humans, so here we are, we only hear from 20 to about 20,000 hertz. Dogs can hear below 20,000 and above. And that's why when you blow a dog whistle, you can't hear it, but a dog can. Dolphins have the same range as dogs. Notice fish. Fish don't go above what? 4,000 hertz. Poor frogs, they can't hear anything. So you could probably sneak up on a frog if you were quiet enough. Same with, well, I would say the same for a bird, but I can't sneak up on a bird to save my life. But you can go look up different hearing ranges for various species. But I thought this was interesting and fun too. So sound can only travel if there is a medium. It has to have a solid, it has to have a liquid or a gas. And I hope we get to talk more about this. And there is an experiment that we can watch. We don't have the materials to do it, but it shows that sound needs a medium. It cannot travel through empty space. And hopefully we get to talk more about that. And then the speed of the sound will depend on the properties of the medium. So if it's a solid or liquid or a gas, the sound will travel differently in a gas versus a solid. And you could test this at home if you wanted to. Go talk to your sibling face to face, but then shut the door and try talking to them through the door. The sound is going to travel differently. Okay. So the speed of sound does depend on the properties. It also depends on elasticity, density, and temperature as well. And then there is a brain pop video here. If you would like to watch it, I'm not going to play it, but you have access to watch this. And it kind of just talks more about frequency and amplitude of sound waves. Now, the next two slides are just some little tidbit informations about how you actually hear sound. If you click this link, it is another video that takes you through how you hear sound. But these are just the basic components. So you have three main sections of your ear. You have an outer ear, you have a middle ear, and then you have an inner ear. And each has a different function. The outer ear, you'll notice over here, kind of funnels into a narrow region, this purple section here. And we know this as the ear canal, and it ends at the eardrum, which is right here, where my pointer is. And sound waves make your eardrum vibrate. Well, the middle ear, so where the green is, contains three small bones, the hammer, the anvil, and the stirrup. And the middle ear will transmit the waves inward towards these bones. Now, behind the middle ear, so let's find that middle ear here, there is a cavity filled with liquid right here called the cochlea. And it's shaped like a snail. So you can see it's kind of looks like a snail shell. And it's lined with more than 10,000 nerve cells. And these nerve cells have tiny hair like structures that float in the liquid. Now, when the stirrup, so let's find that stirrup. So when this vibrates right here, the vibrations will pass to the hair-like structures, sending messages to the brain. Well, the inner ear and the cochlea will convert these sound waves into a form that your brain can understand. And the video linked right here in the text, the title, will go a little bit more in depth with that. And then there's just a bigger version of that model for you to take a look at. And so that's all I've got for you for this. This should help you kind of summarize those relationships between volume and amplitude and pitch and frequency. Okay. Please reach out if you have any questions. You must score an 18 out of 18 on this. You need to redo this until you score an 18 out of 18. Please don't forget to turn it in as well on Google Classroom once you have scored an 18 out of 18. Additionally, you need to go back and complete weeks 2, 3, and 4 of your NTI work. Okay? If you have questions, like I said, just let me know. Hope this helps.